Okay, students, let's discuss the temperature dependence of resistivity and maybe resistance also. Because you know resistance का अगर हमने dependence देख लिया temperature में, so resistivity भी आ जाएगा और resistivity का देख लिया तो resistance भी आ जाएगा. There's a difference, there is a little difference in the formula. So let's write down the formula for the resistivity for us. So resistivity will be m over ne square tau. Is that okay? Now we have three things. One is metal, then we have alloys, and then we have semiconductors. We need to discuss these three basically. So let's start with metals. In case of metal, there is no much change in number density because two factors are very important here. One is N. What is N? Tau. What is N? N is number density. N is number density of free electrons. Then tau is average relaxation time. Average relaxation time याद आ गया होगा मम्मी के थप्पड़ के बीच में दो जो गैप मिलता है वो ही हमें रिलैक्स करने का टाइम मिलेगा और वो ही एवरेज रिलैक्सेशन टाइम होगा. नाउ इन दैट केस द प्रॉब्लम इज इन मेटल्स एंड अलॉयज इन द बोथ केसेस. Yes. So now I want to check whether these two quantities are depending on temperature or not. Because m is the mass of the electron which will not change. E is the charge on the electron which will not change with temperature. So these two quantities are there which can change, which may change with temperature, but the number density does not depend on temperature much, does not change with temperature. In case of both the things, metal and alloys में n ज़्यादा चेंज नहीं होता है, ऑलमोस्ट नहीं होता है with change in temperature. So this factor will go out from this comparison. Now we'll go with this tau only. So this tau is the factor which affecting the resistivity here. Now tell me if you increase the temperature, what will happen to the average relaxation time between two successive collisions? Two successive collision means electron has to go from this collision to this collision. Now there is a gap. When you increase the temperature, which quantity will change? The quantity that is kinetic energy. So kinetic energy will change. So when you increase the temperature, kinetic energy will increase. Because of that, velocity will increase. So this electron will cover this distance quickly. That means the average relaxation time will decrease. So assume that there is a one collision number 1 and there is a collision number 2. So when electron is moving with a certain velocity and you increased the temperature, when you increase the temperature, what will happen? Its kinetic energy will increase, its velocity will increase. Now it can reach faster or it can reach in lesser time. That is why relaxation time decreases. Because of decrease in relaxation time, resistivity is inversely proportional to the tau. So what will happen to resistivity? So resistivity will increase. For what? For metals and alloys. So when you increase the temperature, electron can move faster because they have more kinetic energy, and because of that the collision time between two collisions, that is relaxation time, it will decrease, and because of decrease in tau there will be increase in resistivity. So metal and alloy, if you increase the temperature, in case of metal and alloys, resistivity will increase. This is the basic thing right now. I am just, later on we will distinguish between metal and alloys also. Later on we'll see the difference in the variation of resistivity with temperature in metal and alloys as well. Right now I'm doing as a common thing. Now in case of semiconductor, the problem is, tau will decrease. That is okay, but the problem is, in semiconductor we have covalent bonds, and because of that this number n, number density, because when you increase the temperature covalent bonds will break down, and due to the breakage of covalent bonds this n will increase, and this increase is much greater than this decrease, much greater than this decrease. So the factor on which now the resistivity of the semiconductors will depend is n, not the tau, not the tau. So relaxation time is changing, yes, changing, but more effect is giving by n. That is why when n increases, what happened to the resistivity? So with temperature semiconductor resistivity will decrease, now many a time in examination they ask about conductivity, they will ask conductivity. So please remember this, that reciprocal of the resistivity is conductivity. If you increase the temperature, n is increasing, resistivity decreasing, so conductivity will increase. Is that okay? So similarly you can do for metal and alloys. This is the simple discussion and simple thing you can write in examination. So now I want to represent the same thing on the graph. So in case of metal, resistivity is inversely proportional to tau. When we increase the temperature, tau will decrease, and because of that decrease there will be increase in resistivity, that we need to remember. Now to show this on the graph, we have a standard graph for that, you can remember it. This is the temperature scale and this is resistivity. In examination if they are asking about resistance temperature graph, you just put R over there instead of resistivity. That is a simple thing you can do. So this will be this kind. And then in case of alloys, if you think alloys, what is happening to alloys? Resistivity is inversely proportional to tau, that is okay. The same thing it will be here, but the problem is they have a different property from the metals. So this is temperature, this is resistivity, and they have a difference in the graph as well. So here the graph is more flatter. There is a change in resistivity, but that is not similar to the metal. It is different. So see, what is the difference between the metal and the conductor? So this is the difference. You can recognize large change in temperature can do small change in resistivity. So large change in temperature can do small change in resistivity, because this is the change, total change if I look for. Okay, in case of metal, you see there is a small change in temperature can produce large change in resistance or resistivity. Large change in resistivity. So in case of metal, please remember this, small change in temperature can produce large change in resistance or resistivity, and in that case it's just quite different, that large change in temperature, and this is a quite good property for the alloys. Large change in temperature can produce small change in resistivity. Please remember this. So there is a small change in resistivity. This you need to know. And the third thing, which is semiconductor. So how to so in case of a semiconductor, as you know, resistivity is inversely proportional to the number, as you need to increase, like if you increase the temperature, it will increase the number density, and because of that resistivity will decrease. So this will be an inverse relation for us. This is temperature and this is resistivity. So simply you can just draw in that way. So this is for semiconductor. These three graphs, I'm just drawing it for your reference. That one is resistivity. Okay, tell me which one is this one, and name for that also. So it will be a quick revision for you. So this is alloys, and this is metal. This is for metal. So please remember this. This is very important. Actually, direct questions used to come like draw graphs for metal, alloys, and semiconductors. And so we have another topic, that is limitation of Ohm's law, and one marker or maybe assessment region will come from this. So let's start with this. So first point is like V ceases to be proportional to I. They are trying to say that V is linearly proportional to I, but in few cases it does not valid. So why it is not valid? So take an example, a conductor, we are giving a voltage to it. If we give the voltage at a certain voltage, heat will produce because of flowing of current, and this heat will rise the temperature of the conductor. Because of change in temperature of the conductor, resistance will increase. So now voltage does not depend directly to the current. So there is a variation which is not linear. So this is what they want. Same graph is shown here. So you can refer this, it is changing towards the voltage. So more voltage will be there. So like for example, at this current, the voltage should be this one, but now voltage will be higher. So why voltage will be higher? Because current is same, but because why voltage is higher now? Because of current there will be I square RT. So that is the heat. Because of this heat there will be increase in resistance. So at this current, same current, more resistance will be there, and because of that more voltage will be there. Is that okay? So this is how now it is not linear. So in that case Ohm's law is not valid. Now next thing is relation between V and I depends on the sign of V. So we have few devices like diode. This you will understand more in the last chapter, that is semiconductor devices. What you need to understand right now, that is in a certain direction, like if a diode we have and we connect it in this way, like this is the connection, like this is the positive terminal. Right now I'm just giving a name to it. This is the P terminal of the diode, and this is N terminal of the diode, and this is positive and negative. If you connect in that way, so its behavior will be this way. So it is given, you can see. Now if I connect this diode, the same diode, in another way, that P side is connected to negative and N side is connected to positive, then its behavior will be different. So that is that is the thing they are saying. Relation between V and I depends on the sign of V. So if we switch the V, for metals it is, for metal it does not depend, but in case of diode or semiconductor devices it does matter. Is that okay? So second is this. Now the third is the relation between V and I is not unique. That is, there is more than one value of V for the same current. So this is again for the semiconductor. So we have a special semiconductor, that is gallium arsenide. So Ga we will use to write GaAs, gallium arsenide, and for which we have IV graph here, and in that graph you see there are the same values for the same current. There are same value of voltage for the same current. So two different voltages have the same, two different voltages at the same current. So this is again a limitation of Ohm's law. Ohm's law is not valid here. Okay, in this graph I just want to draw your attention here for a special case. The question which is very famous based on this graph is, why Why this region? Why this region is negative resistance region? They used to ask why, or they can ask which region. They can mark A, they can mark B, they can C, they can D, they can mark D. So out of these four regions, which one is the negative resistance region? So negative resistance region is C. Answer is C. So why it is negative resistance region? Because current is decreasing. Because current is decreasing. Because current is decreasing. It does not mean that resistance becomes negative. Please remember, it does not mean that resistance becomes negative. It means that resistance, it means that there is decrease in current. There is decrease in current. So that is why we are saying negative resistance region. Is that okay? So hopefully you understood these 3 points, because this is very important for assessment and reasoning. So